We are going to study Coulomb's law, and while studying Coulomb's law, we are going to note down the expression that Coulomb's law gives us for the force between 2 point charges. So here we see 2 point charges Q1 and Q2. The distance between the 2 point charges happens to be r. Now, Coulomb noted empirically, that is experimentally, that the force between these 2 point charges F is proportional to the magnitude of the two charges. So F was proportional to Q1, Q2. He also noted that F was also proportional to 1 over r square. So r being the distance between the two charges, F was also proportional to 1 over r square. So he came up with an expression which reads like this: F is equal to K times Q1 Q2 over r square. So this is the expression that we have, which is the force expression representing the force between the 2 point charges Q1 and Q2. Here K, the proportionality constant, can also be represented alternatively as K is equal to 1 upon 4 pi epsilon naught. Epsilon naught is a constant that is called as the absolute permittivity of free space. The value of epsilon naught in SI units happens to be equal to 8.85 into 10 raised to minus 12 and from the formula for the force we can say that this is going to be Coulomb square Newton minus 1 meter raised to minus 2. So this is the SI unit value for the absolute permittivity of free space, often called as just the permittivity of free space. Now if we substitute this value of epsilon naught in the expression for K, then what do we have? We have the effective value of K in SI units to be approximately equal to 9 into 10 raised to 9 in SI units. So this is important to be known. Now let us see what happens when we are wanting to express the Coulomb's law that we have in the vectorial form. So in the vectorial form, what can we write? We can effectively write F21, that is the force on charge 2 because of charge 1. F21 is going to be equal to K times Q1 Q2 upon r square, and then we have this unit vector r1 2. So the force on charge 2 because of charge 1 is going to be given by the same expression, but then we have got this unit vector r1 2, which points from the location of charge 1 to the location of charge 2. Note that if both the charges are positive, then the force is going to act outward. So the force is going to be repulsive. Similarly, if both the charges are negative, the force expression gives a positive value and hence the force is still going to be repulsive or outward. Also note that if either one of the charges is positive and the other is negative, then in that case the expression k q1 q2 upon r square will be a negative value. That means the force will be attractive. That means charge 1 will be attracting charge 2. So by fixating the direction of unit vector r12 cap to be going from charge 1 to charge 2, we automatically also fixate the signs and the effective repulsion or attraction between the two charges. So the sign of the force automatically gets fixated. So this is something to note. This is the vectorial representation. Now if we would like to actually write down the force on charge 1 because of charge 2, we can similarly write it down as force 1 2 vectorially. Here also we can write this down as a vector. So force 1 2 vectorially is going to be given as k times q1 q2 upon r square, and here the vector that we'll write is r cap 2 1. So this is the charge q1, this is the charge q2. R cap 2 1 is a unit vector that points from q2 to q1, whereas r cap 1 2 is a unit vector that points from q1 to q2. So this is how we vectorially represent the force. We can clearly see one fact, that force 2 1, that is force on 2 because of charge 1, is negative of force 1 2. This can be very clearly and easily observed.